Okay, so we're recording. Physics 211, Lecture 12. And so we started with the VVOX, which was the question about whether an object can have non-zero energy even if it has zero momentum. And the answer is yes, it can. For instance, if it has only gravitational potential energy, but no momentum. So motionless, but perched up on a shelf or somewhere up in the air above the ground, that would be a situation where you have non-zero energy but zero momentum. Okay, so today's topic is known as waves. Today we're going to talk about waves. And so we must begin by first defining what a wave is. So a wave is a disturbance. It is a disturbance that propagates through an elastic medium. Okay, so in as much as you have a medium that is elastic, that means it's kind of springy, right? You can stretch it and compress it a little bit, right? So as much as you have such a medium, that medium can propagate disturbances through it, and these disturbances are known as waves. And there's many examples of different types of waves that we encounter in our experience. For instance, there's water waves. These are the waves that kind of oscillate up and down and move across the ocean. When they become very large, we start calling them tsunamis, right, or tidal waves. There's also mechanical waves. So these are like the waves on a guitar string. Like when you pluck a guitar string, what happens is the string begins to oscillate up and down, back and forth. And what's happening is that it's actually emitting waves that sort of propagate up and down the string and bounce back and forth, and cause the string to wiggle back and forth and produce the sound. Then there's of course sound waves. That brings us to sound waves. That's another type of wave, and what that is oscillations in the density of air, for sound waves that pass through the air. So what's happening is you've got this disturbance in the density of the air, the local density of the air that is propagating through the air. So air does kind of act like a spring that can be stretched and compressed, and when it does that, in a pattern that's a disturbance that propagates through, we call that a sound wave. You can also have sound waves in solids and other materials. As long as you can admit a disturbance that propagates in the form of increases and decreases in density that propagate around, then you're admitting a sound wave. That's all a sound wave is. It's just a kind of a disturbance in the density of the material that it is propagating through. So for today's lecture, though, what we're going to mainly be focusing on is mechanical waves. So these are the type of waves that exist, like if you play guitar. I know at least one of you does play some guitar. What you're doing is you're strumming the strings of the guitar. I play a little guitar myself. And what you're doing is you are exciting waves that propagate up and down the string. So these are really mechanical waves. And so what we're going to do is we're going to derive the physics of these waves, and we're going to show that this physics that describes these waves is actually generalizable to pretty much any other type of wave. So actually, before we get into the mechanical waves on the guitar string, I should point out that waves have a very important property. They have a very important property. So waves are substrate independent. So what that means is that whether you're talking about sound waves, mechanical waves, water waves, electromagnetic waves, the physics that describes how they propagate, how they oscillate up and down and move through space, um, that physics is exactly identical. The details of how you made the waves is completely unimportant when it comes to describing how they behave. Okay, so there aren't that many phenomena within physics that have this property of this substrate independence, and so that's why it's important to stress that it does apply to waves. So even without knowing the details of how the wave came about, if you understand one type of wave, so we're going to understand today mechanical waves just in one dimension, you can generalize that understanding to pretty much every other type of wave because of this property that they have of being substrate independent. So without further ado, let's get into how waves behave, let's say on a guitar string. So a guitar string is kind of like this. It's basically a piece of string that is fixed at either end. Okay, so this is fixed at both ends. So this is a string fixed at the ends. All right. And so what we're going to do is we're going to imagine that this string has it's under tension. All right, it's under tension, so it's stretched in between these two endpoints, and we're going to imagine that you grab a hold of a section of it, with your hand, and you pull it, and then you let go to see what happens. All right, so you're gonna stretch it a little bit, and then and let go. This is what it means to pluck the string. And so what we're going to do is we're going to imagine that the little place that you grabbed a hold of, right, is a little section of the string that has a length of delta x. Okay, and I apologize for only using one color here, but can't seem to find my other markers here. Not sure where they went. Anyway, so it's fixed at each end, and we're going to focus our attention on this little segment here. Oh, you know what? I suppose I should make it so that you can see this better. Yes. So the question is, for sound waves, is air the elastic medium? The answer is yes. For water waves, it's water. Okay. For for this wave that we're looking at here, mechanical waves, it's the string itself. It's stretchy, right? And it can stretch and compress, right? And so it serves as the elastic medium. Now, the one exception to this rule that I'm saying what a wave is the electromagnetic wave. That has the property of being able to fly through empty space. Okay, so electromagnetic waves, they do have this quirk about them that they can fly through space. They don't seem to need an elastic medium to propagate through. But if you think of the electric field or the magnetic field as acting as an elastic medium, like you can stretch and compress a force field, if you will. If you think of it that way, then it makes sense, and you can think of electromagnetic waves as flying through an elastic medium. But we're not really going to dwell on that for today. We're mainly going to dwell on this, which is the mechanical waves that propagate up and down a string. So imagine you've got this section here and you pulled on it, and now we want to look at what the forces are on this thing. So maybe if you'll excuse me a moment, I'm going to see if I can find my other pens, because I hate just using the same color for everything. Okay, sorry, I didn't mean to slam the door there. All right, so so what we're going to do is we're going to imagine a coordinate system, right? So this is the x direction. So we're going to imagine a coordinate system that looks like this. Okay, so this is y, that's your y-axis, there's your x-axis. And so now let's suppose that I've grabbed a piece of the string and I've pulled it. And so I'm going to draw this little segment of the string that now I'm holding between my fingers. All right, so there's my little segment of string. That's my segment of the string with length equal to delta x. All right, so that's my little segment that I got. And then if I look at it, well, I want you to imagine that this string is under tension. And so the force of the tension in the string, we're going to call that F sub t. So here, I'll indicate that over here. So the tension is F sub t, like that. F sub t. That's the force of tension that's in the string. And then, so now when I pull on this, right, there's going to be tension pulling this way and tension pulling that way, both at the same time on this thing. And so, and we're going to imagine that I'm not pulling it so far, I'm only pulling it a little bit, so that the angle I'm making is small. And so that'll allow us to make a certain approximation that I'll explain in a moment. So what I have here is I have a force of the tension pulling back like that. We're going to call this F1. Okay. And then there's a force pulling back on the rest from the rest of the string the other way. We're going to call this F2. Okay. And then we're going to break it down into components. So we're going to break it down into components. So we're going to have, so this has a horizontal component that looks like that, and a vertical component like that. Okay. And then this one is the same. It has a horizontal going that way and a vertical going that way. All right. And so you see that, you know, they're in opposite directions. They're in opposite directions. And so you can also imagine that what I have here is an angle, and I'm going to call that theta 1. And here I have an angle, we're going to call that theta 2. All right. And so we're going to make the approximation that these angles are basically small. So they're small enough that there isn't really much of a difference between this F1 vector and the FT vector here, right? So we're imagining that this horizontal component is just FT. So here I'll draw this component and this component are approximately F sub t, and this component has the same thing about it as well. Okay, and so this will be true as long as these angles are small. So we're not deviating this string very far in order to play it, in order to pluck it. Okay. So let's see, what else we got here? All right. So now, so again, you know, we're also going to ignore the fact that, you know, we've twisted this out of position, so now it's at an angle. We're going to assume that the displacement between the ends of this segment that we have between our fingers has the same width as the segment itself. And this again will be true as long as these angles are small. Okay, so now I'm going to write out mathematically what I sort of sketched out here. So if the displacement of the string is small, if the displacement is small, then we would say that the tangent of theta 1 is going to be the ratio of this to this, opposite over adjacent. And so, by the way, I'm going to call this component, I'm going to call it F left, and I'm going to call this component F right. This is to the left, this to the right, right? So F left is this one, F right is that one. And so the tangent of theta 1 is going to be F left divided by Ft. So I said Ft, approximately Ft, FL over Ft, tangent of theta 1. Tangent of theta 2, guess what, is going to be Fr over Ft. Okay. Okay. And so that's now the angle. This is describing the angle here and the angle here. So we got tangent of theta 1 is this ratio, tangent of theta 2 is this ratio. All right. Now, if you think back to your calculus class, and you know, if you were paying attention in calculus, you would be accustomed to the idea of the tangent of an angle. The tangent of an angle is pretty much equal to the slope. It's equal to the slope at that point where you're defining the angle. All right. So a tangent is a slope, right? It's rise over run, right? Rise over run is a slope, right? So we're talking about this angle here, right? And so you have some function that, you know, smoothly varying. And so at this point, you can draw a tangent line to it, and then it makes an angle with the x-axis, and you take the tangent of that angle, and that's the ratio of how much this tangent line rises over how much it goes across. And so a tangent is really a slope. Okay, you should be accustomed to this idea from having paid close attention in your calculus class. And so the slope, so since this is a slope, we also know that a slope is a derivative. So we would say that the derivative at location x1 is going to equal FL over FT. Okay, so, and we can write a similar expression for FR. So if we just for a second, let's go back to our picture here. So we're going to call this location over here, we're going to call this x1, and this location to the right of the place where we're plucking the string, we'll call this x2, okay? And so we have this angle here that's defined at x1, which is theta 1, and we have theta 2 defined at x2. And the tangent of those two angles is simply the slopes of the shape of the guitar string at those two locations, right? And remember, it requires a slope. It's no longer horizontal at those two locations because we've grabbed a piece of the string with our fingers and we've pulled it out of alignment, right? This is how we pluck a string. You grab the string and you stretch it a little bit at that location. You make it deviate away from being horizontal. That's how you pluck a guitar string. You make it deviate away from being horizontal. Okay, so now let's do the same thing at location x2. So we have location x2, we have the derivative at location x2, and that's going to be FR over FT. Okay, now let's apply Newton's second law. Let's apply Newton's second law. So Newton's second law says, Newton's second law basically says that the net force is equal to the mass times acceleration. So we can apply this idea by asking ourselves, when I let go of that guitar string, what is its acceleration going to be? All right, given that it is subject to these forces of tension to the left and to the right of it. Okay, so we would construct that as follows. We would say that the net force is going to be the force to the left, sorry, the force to the right, which is positive, and the force to the left, which is negative. So you take, you add them, you get the net force. So, so if we rewrite Newton's law with this in mind, we would have FR minus FL is equal to m d squared y dt squared. So y now is the y coordinate of that segment of string that we're plucking. Similar to this y, it's the same y here. This is the position, right? So we're taking the slope of the string, right? And so that is the position along y that the string has, at a given point along the string. So that's what this y coordinate is telling you. And so here's Newton's law with the forces in there, mass times acceleration. And so, but you see here, this is the same thing if we use the fact that FL is the same thing as the slope at a given location times the force of tension at that location. It's the same tension over the whole string, so this is just a constant. So we would rewrite this as follows. It would look something like this. Ft times dy by dx at location 2 minus Ft times dy by dx at location x1 is equal to m d squared y dt squared. And so, by the way, this mass in here, right, we're only talking about the mass of that little segment that you're holding, right, that has length delta x. So I'm actually going to call this delta m. I'm going to call this delta m, and I'm going to say that this is the mass of the segment of string with length delta x. That's what delta M means. Okay. And so we're interested in what is the acceleration of that little segment, right? So as it accelerates, of course, it's still stuck to the other, it's still connected to the other parts of the string, right? So it's going to drag them along with it, right? But and so that's going to happen. But you know, for the purposes of this problem, we're just focusing our attention on what is going to be the behavior just at that location where we are plucking the string. Okay, so that's how that comes about. So so let's see. So I have this equation now, and so you see here, what I have is I have a slope at this location to the right and a slope to the left. And I can factor out the ft. Let me do that. So I factor out the ft, so I get dy dx x2 minus dy dx x1 is equal to delta m over f sub t d squared y dt squared. Okay, so you see I'm looking at the difference between two slopes. The difference between two slopes. So we're actually looking at the change in slope. Okay, so if a slope is a derivative, then the change in slope is a second derivative. So what I have here is I don't completely have a second derivative. What I have is a difference between two slopes. But if I were to divide this by the distance between those two locations where I'm calculating the slope at each location, then I kind of have a ratio of the change in slope to the distance over which that change happens. And that is kind of the definition of a second derivative. A second derivative. So, so what's happening is I basically have, so if I have this, if I have, here, I'll do this over here. If I have dy by dx at x2 minus dy by dx at x1 divided by delta x, that is basically equal to, or I should say it's approximately equal to d squared y dx squared. And so this becomes equal, this approximation becomes equal in the limit as delta x goes to 0. If you take the limit as delta x becomes 0, then it becomes exactly equal to the second derivative at that point, right? At that point, that's sort of halfway in between x2 and x1, right? And so as you take the limit as delta x goes to 0, these two become very close together, and pretty soon they're on top of each other. And then what you've done is you've evaluated the second derivative of y with respect to x at that location that's in between x2 and x1. So we can basically go back to this equation here, and we can now write what we really have is delta x times d squared y dx squared, and that's going to equal delta m over f sub t d squared y dt squared. Okay, so now what we see is happening is now we have a function, we basically have a differential equation for a function y, but you see here we're taking a derivative with respect to x, and here we're taking a derivative with respect to t. So in the end, this means y has to basically be a function of both position along x and time. All right. And so what we want to do when we take these derivatives, we only want to take it with respect to that particular variable in question. All right, so over here, we're basically treating time as a constant when we take the derivative with respect to x. Over here, we're treating x as a constant when we take the derivative with respect to y. And so this is basically to introduce the concept of the partial derivative. The partial derivative. So that basically means, well, here, let me say, but y is actually a function not only of x, but also of time. So these derivatives should really be expressed as partial derivatives. So we would write instead of this, and this, we write this. We use a partial symbol. This is a partial symbol. So this is saying that you're differentiating with respect to a variable, but you're keeping all other variables constant as you do that differentiation. That is known as a partial derivative. So we write this, and like that. So these are known as second partial derivatives. Second partial derivatives. Okay. So so when you do these derivatives, again, y is a function of both x and time. So when you take the derivative with respect to x, you're treating the time that's in there as though it's a constant. So it's as though you've got these waves, propagating on the string as it's, it's vibrating and doing its thing, right? But what you do is you're interested in knowing what its curvature is, at some moment, right? The second derivative with respect to x is the curvature. So you're interested in knowing what the curvature is. And so what you do is you say, well, I want to know the curvature, but it's moving. What do I do? Well, you take a snapshot of it, right? So you're freezing it at a given time. You're treating time as though it's constant, and then you're taking the derivative of the snapshot that you have at that time. Okay. And then for this guy, the curvature may be varying, all along the along x. So what you do is for this is that you focus your attention on just one location on the string, just one location, and then you're looking at how it moves, and you're saying, well, with respect to time, how's it moving? How much acceleration does it have with respect to time, just at that one point? Okay, that is how you do partial derivatives. You treat the variable that you're not differentiating with respect to as though it is constant. So these are second partial derivatives. Okay, so now what we're going to do is we are going to say, we're going to rewrite our equation the way it's supposed to be written. And so our equation is going to look like this. So let's see, it's going to be delta m over delta x ft in the denominator. And that has to equal, okay, And so now we can define mu as equal to the mass per unit length of the string, right? So like the amount of mass you have per unit length of the string. So that's how heavy the string is, right? So if you've ever played guitar or any stringed instrument, you'll see that the different strings that produce the different sounds, they have a different weight, right? So like if it's a thicker string, it has more mass per unit length. And so it has a higher value of this mu parameter to characterize it. Okay, so we're going to define that. And so now our equation looks like this. Now it looks like this, mu over ft. And that, okay? And so this is known as this equation. So anytime you have a partial differential equation of this form, where you have curvature equals a constant times acceleration. So a curvature, the curvature at any given point of a guitar string is proportional to the acceleration at that point. Okay? And so this is true of waves that are propagating on a guitar string. As it vibrates, right, it's emitting these waves that propagate back and forth. And so the curvature at any given point is directly related to the acceleration of that point, right? And we're talking about vertical acceleration up and down along the y dimension. Okay, so these are what we call transverse waves, because the oscillations or the motion of the wave is transverse to the propagation axis. Okay, and so this constant here, this turns out is 1 over the wave speed squared. So the speed at which the waves are propagating up and down the guitar string you take 1 over that speed, square it, and that's the proportionality constant that relates the curvature to the acceleration on your guitar string. All right, so this right here, so probably what you normally see in your physics textbooks is you see something that looks like this. And so this is known as the one-dimensional wave equation. Okay. So now, so how do you solve this equation? Well, the way you solve it is you solve it by ansatz. So what does that mean is that you ask yourselves, well, you know, I need a function that is a function of x and time. All right, I need a function that's like this, and I need it so that if I take 2x derivatives of it, then I basically get the same function as I get when I take 2 time derivatives of it, except it's the same except related by a constant, right? And so turns out there aren't many functions that have this behavior. Turns out sines and cosines actually work very well for this purpose. And so what you would do is you take a guess and you would say that my equation is going to look something like this. for my solution, okay, and then you plug it in, right? So you got these parameters in there, and then you plug it into this, and you see what happens, and then based on trying to get the left and the right hand side to equal each other, that will constrain what the values of the three parameters are going to be. All right, that's how you solve an equation by ansatz. So so I think on the homework, you're actually going to have to try this out yourselves. So I'm not going to show you exactly how to do it. You'll have plenty of opportunities to try it on the homework. But I will label these. So you can see this is basically a sine function, right? So it oscillates both in space and it oscillates in time. Okay, and that's exactly what a wave does. It has an amplitude, which is the size of the oscillation. Okay, it has a wave number, which is equal to 2 pi divided by the wavelength. Okay, it has an angular frequency. It has an angular frequency, which we understand. And then it has this, which is known as a phase shift. So this quantity will only be non-zero if this is basically to specify your initial conditions. So what shape did this guitar string have when you started looking at it? That is to say, what shape did it have when time was 0? Okay, so that's controlled by whether by what this value of this variable is. All right. If at time 0 the if at time 0 it had a shape of a pure sine wave, that started at x equals 0, then this phase shift would be 0. But if it had some other shape than that, like a shifted sine function, then this phase shift would not be 0. Okay, and so then in the 5 minutes I have left, I will show you what is needed for this ansatz to actually work. And what is needed for the ansatz to actually work and satisfy the equation is if the square root of ft over mu is equal to omega over k. Okay, so this has to be true for that functional form that I showed you to actually satisfy the equation. And so what people typically write, or actually not people typically do this, what is correct to do is you can say that, let's see, what do we do here? So what you would do is you would write, you can rewrite the function I gave you, y of x comma t. You can rewrite it like this. So now I'm going to rewrite it in terms of ft and mu. Okay, and so that's going to look something like this. I'm going to factor out the omega. No, sorry, I don't want to do that. Don't want to do that. I want to factor out the k, the wave number. I'm going to factor that out. And then inside my parentheses, I have x plus or minus vt plus my phase shift. Okay? Yeah. All right. So that's what I have. Okay. And so this works if V is equal to the square root of Ft over mu. So this is now the tension in the string, and this is the mass per unit length. So, and so the, 1 over the square root of that is the speed at which it is propagating. So you can see here, what we've got here is we've got the, this is the x coordinate of any position along the string. And so you can see that that is a sine function. So so the shape of the string is shaped like a sine wave, like that, but it's a sine wave that is moving in a particular direction, either away or toward you, with this speed. And so the plus or minus, this controls whether the wave is traveling away or toward you. So wave can be moving to the left or to the right. Okay, so if it's moving to the right, it's the negative that you would adopt, and if it's moving to the left, it's the positive uh, solution that you would adopt. And so that really pretty much sums it up. So if you ever have a chance to inspect a guitar, maybe you have one yourself, or you can you play one yourself, or maybe you know someone who does. You can see that the guitar strings, the speed at which they vibrate has to do with the tension that you apply, right? So there are pegs on the ends of the guitar string for you to tighten up the tension. And it also has to do with how heavy the string is. So you can look at the guitar string, you see some of them are much heavier than others, okay? And so what's different is that they have they have different wave speeds, and as such, actually, they have a different, they produce a different sound, because the speed of the wave sort of determines how much it hits the air to make a sound wave, and then the more frequently it's hitting the air to make these pulses of air pressure that go to your ears, if it's more frequent, it sounds like a higher pitch, and if it's less frequent, it's a lower pitch. Okay, so this is how it all works with your guitar, or indeed any stringed instrument works this way, thanks to this relationship that we have. Okay, so I think we are about out of time, so I'm going to stop it there, and yeah, I think that's it. So if you need help or whatever, have questions about homework, you are welcome to come to my office hours. I'll be holding office hours at this channel, this Zoom channel, at let's see, at 5 p.m. And I'll be holding them again at 11 a.m. on Thursday. All right, yes, thank you. And so we'll see you next time. Thank you.